Hi, I'm Lucy from Zhejiang University. Today, let me talk about our recent work, an efficient triage planner for tractor robots in unstructured environments. Okay, autonomous driving has gained tremendous interest in recent years when transporting large cargo. Tractor systems such as semi-trucks are widely used due to their greater transportation capability. This tractor robot consists of a drivable tractor and multiple non-drivable trailers connected to hinges. In this work, we study the motion planning problem of this kind of robot. The hinge structure introduces complex kinematics with underactuated trailer constraints. Its coupling with the non-holonomic constraints of the tractor requires a planner capable of handling more equation constraints. Okay? Each trailer adds three dimensions to say space, leading to a high-dimensional third space for tractor planning. And the hinge structure also caused a deformable shape, making collision avoidance harder. Recently, differential flatness and polynomial representation have shown great efficiency in trajectory planning for car-line robots. So, inspired by this, firstly, we try to derive the differential flatness of the checked traders. A previous work shows the last trader's position and flat output, but as the number of traders increases, the nonlinearity of the system grows dramatically, and this method cannot be extended to more general checked trader configuration. So we turn to another way for the Churchill parameterization. We introduce second arguments to avoid the singularity of the differential flatness for the shader, and use shader position and yaw angles of all shaders as our representation, making it universal and scalable or to arbitrary shader configurations. And we can see at zero speed, at zero speed, the differential flatness will cause zero denominator. Use standard arguments can avoid it, but introduce these three new constraints. For tractor, it's real for the forward velocity to be zero. Thus, using polynomials to represent the trajectory poses a greater challenge to optimization because of the need to impose equation constraints at each time step. So to select this equation constraint and facilitate optimization, we define a selection arc length. Physical values can still be derived analytically. The final trajectory is determined by piecewise polynomials. This is the formulation of our trajectory optimization problem. The constraints include dynamic constraints, continuity conditions, dynamic feasible bounds, and bound conditions. So for safety, we use an SDF-based collision avoidance constraint where we model each vehicle as a circle and vary the sign distance file. This is a better way than corridor-based method because safe corridors need to be constructed for each vehicle separately, which heavily depend on good initial values. Our SDF approach directly deforms the trajectories in continuous space and tolerates polar initial gases. Specifically, we can only use one hybrid star for the tractor, and then obtain the state trajectory of the trailer through approximate thematic integration. As shown in the figure, we can efficiently gain a feasible trajectory without a very good initial value. Here we give a detailed comparison with OCPSDC, a SOTA corridor-based and NMPC-based method in a parking lot scenario. Since the presence of narrow spaces and large terms in this scenario, it's difficult to provide good seed for the front-end path for corridor generation for every vehicle in the robot. The OCP ST causes the robot to take bigger turns and doesn't make for the use of collision-free area at the edge of the parking space. As shown in this table, with the greedy front end FC2 MHA, our method achieves a total planning time of only 0.36 seconds versus over 4 seconds for OTP and CC with Hybrid A star. So we also conduct ablation studies to validate the importance of selected arc lengths. Without it, we need VS as minimal speed constraint to avoid the singularity. But optimized geometry speed constraint violations at the start and the end phases when VS is too small, and extremely discontinuous speed and large tracking errors when VS is too big. We conduct the tracking error test using a MPC controller in the demo. We further perform large-scale benchmark comparisons with randomly generated obstacles. The line graph shows that our method consistently consumes the least optimization time for different numbers of traders and planning horizon. This figure shows the effect of different initial value selection methods on the success rate of the three different methods when the obstacle density is needed. Our method shows the best performance. The tracking error experiment further demonstrates the superiority of our method compared to OCPSDC. We attribute this to high-order continuous polynomial triage representation. Compared to methods employing discrete motion process, our approach essentially guarantees the continuity of the state and finite dimensional derivatives, making our triage closer to real physical motion process. To validate our method in real world, we built two kinds of track robots. They have different kinematics. The system includes level sliders and then using computers. For the small one, we use a reflective speaker-based localization. For the big one, we place a LiDAR and a round Leo on each shader separately, aligning the wood frame with the Leo running on the trailer. We conduct four kinds of experiments, one indoor and three outdoor. In the indoor experiment, we set up the tractor robot to transport, load, and unload cargo to demonstrate the possible real-life applications of the proposed navigation system. The first outdoor thing is the exile by the non-motorized parking area. This environment is filled with different kinds of obstacles, include cube-shaped, cylindrical carts, bicycles, e-bikes. The robot needs to constantly replan to avoid obstacles and traverse these narrow passages. And in second outdoor scenario, the robot is required to load some cargo and drive into a building by approaching predetermined waypoints. The robot perceives the world through the local traversability map, updated in real time, and continuously plans to avoid unknown obstacle along the way. Eventually, it enters the building by triggering an automatic door. The third outdoor scenario is for the general trailer. We place e-bike rotary boxes as obstacles on the path of an industrial park and set up a cargo area. The robot is requested to avoid obstacles to reach near the cargo area. After staff load cargo, is required to continue traversing the obstacle areas. That's all. Thank you for listening.